All right, so maybe you went home last night and started thinking about what type of scenario this could be. Looks like we've got Dennis the Menace right there. Dennis the Menace is acting all innocent at the base of a ladder. And we got this ladder leaning against this wall. And we've got like Shaggy from Scooby-Doo's brother or something all tripping out. I don't know if those are glasses or that he's just, you know, tripping on something. But he's like doing calf raises on the second to top rung of this ladder. He's not even like supporting himself on the arch of his foot. He looks like he's got his toes on there. And he's kind of just without, look at those calves. I mean, they're not even big, but he's able to support himself nonchalantly right there. So, and if you imagine, what is he doing up there? Well, if you just extend this wall straight up, he's freaking staring at a wall. So, yeah. I don't do drugs, guys. Don't do drugs. All right. So anyway, here's the scenario. A 10-foot ladder, a fixed ladder, is leaning against the vertical wall. The lower end of the ladder is being pulled away from the wall at a rate of 2 feet per second. I wonder who's responsible for that. Okay? When the lower end of the ladder is 6 feet away from the wall, we're going to answer all these questions. How fast is the ladder sliding down the wall? How fast is the angle between the ground and the ladder changing? How fast is the area of the triangle formed by the walls and the ladder changing? And what's the acceleration of the ladder down the wall? All right, so what we're going to do is draw the picture. The picture is kind of already drawn for us. It looks like we've got a triangle here. And you can label them whatever you want. We've already kind of introduced the value of x. Since that distance is changing, we'll call this y, since it's called y already. That is a variable. It's changing. And the hypotenuse, do you need to call the hypotenuse, which is the ladder side, do you need to call it h for hypotenuse, or can you just leave it as 10? Very good. You can leave it as 10. So anything that does not change throughout the life of the problem is a constant, and you don't need to introduce another variable for it. So 10 is staying the same because it's a fixed ladder, but x and y are changing. Okay, so now we can, now that we have it labeled, we can find our snapshot moment and then talk about what the rates are going to be in math speak. Sorry. When the lower end of the ladder is 6 feet away from the wall. So that's going to be when what variable is 6? Yeah, x. So our snapshot moment, I'm going to draw kind of a big camera here. It's going to be when x is 6. We might be able to discern soon enough what y is at that moment, so I'll just kind of leave it open. Maybe we'll need it, maybe we won't need it. But now we'll write the rates. It's being pulled away from the wall at a rate of 2 feet per second. If you're ever given something like that, you can assume that it's a constant rate, because it doesn't say, you know, at 2x feet per second. So assume that it's being pulled away from the wall at 2 feet per second throughout the life of the problem. That is directly going to affect which of these variables. If it's being pulled away at the base of the wall, and that's directly affecting x, yeah. So that is going to actually be dx dt. And is it positive or negative 2? Positive. Why? X is getting bigger. Right. X is increasing. Good. Just looking at it, y is getting smaller, right? As it's being pulled away from the wall. So dy dt is going to end up being a negative number. All right, so that's all we had. So now we can move on to part A. How fast is the ladder sliding down the wall? So we want to give ourselves a target. We're looking for the rate of change of what variable? Y. Good. So dy dt is our target. That's the rate of change of its position along the wall. And so ultimately, I'd like to relate the rates, dx dt and dy dt together. But before I can relate their rates, I got to relate their quantities. So in this diagram, how can I relate x to y? Pythagorean Theorem. So assume that this wall and floor were built by not the same people who built the new annex in this building. Assume that they're at a right angle to each other. And why do I say that? If you go into Miss Smith's room, right here on this pillar on the other side where the wall meets up, you can see it right here. That gap, as you follow it up, gets bigger and bigger and bigger. So something's not plumb and square. But we can assume this one is plumb and square. This guy's plumb crazy, and this guy looks like a square. All right. Pythagorean Theorem. X squared plus y squared equals 100, or 10 squared. Yeah, very good. So as we saw yesterday when we had the Pythagorean Theorem, if we're looking for dy dt, do we have to solve this for y before we differentiate? No. The only benefit to doing that is if you do solve it for y, you're not going to need to know the y quantity at a given moment. You'll just have dy dt equals. But it's easy enough to find y at the moment. So instead of dealing with a radical and a chain rule, we'll just take the derivative as it sits right here. So we get 2x times the chain rule dx dt plus 2y times the chain rule dy dt equals 210 d10 dt? What? I don't know. What is it? 0. Yeah, it's 0. Good. The ladder length doesn't change. That's nice. And you can also then multiply everything through by a half or divide out the 2 just to make the numbers a little bit smaller on the calculations. But there you go. You have 4 unknowns. It's not a requirement to solve for dy dt before you plug in. Okay, you could plug in and then solve. So that's what I think we're going to do. All right, let's go for it. We'll say when x equals 6, we'll plug in and we get 6 times dx dt, which is positive 2, plus y. Oh boy. Okay, we don't know what y is. We can find it though, yeah? So if you want to come over here and label the snapshot moment, x is 6 at the moment, and we've got y, we need to find y. So if you don't recognize it as a dilation of a Pythagorean triple, that's what this equation right here is for. That's your position equation. So some of you all already know it. That's fine. I'll just assume that we don't know it. So I get 6 squared plus y squared equals 10 squared. So y ends up being plus or minus the square root of 100 minus 36, which is, do we want the minus one here? No, it's a distance, so it'll just be positive square root of 64, which is 8. And some of y'all did say it's your 3, 4, 5 right triangle, and it is. It's your 3, 4, 5 right triangle that is dilated by a factor of 2. All right, so you may have to go out and find a little quantity before you can evaluate it, but now that we have it, we'll plug it in, and we got dy dt, which is the unknown we're looking for, equals 0. So now you're going to get 8 dy dt equaling negative 12 when you bring the 12 across, and then you solve for dy dt, and you get negative 12 eighths, which simplifies to negative 3 halves. All right, so the sentence would be, when the ladder is 6 feet from the base of the wall, the ladder is sliding down the wall at a rate of 3 halves feet per second. Yeah, feet per second. Very good. That's it. The ladder is sliding down the wall. So you're allowed to do that. You don't have to say the height of the ladder along the wall is decreasing. You could. You can kind of clean it up a little bit with some refined language. The ladder is sliding down the wall by positive 3 halves feet per second. And because this is our last answer, it's a numeric. Just make sure you put units on your final numeric answer. All right, cool. Interesting. That's part A. Part B now. How fast is the angle between the ground and the ladder changing? So if you come back over here to your diagram, you got to identify the right angle. That's this one here. It's changing, so we need to call it a variable. What variable do you want? Theta is a good use of a variable, yeah, for an angle. We'll keep it as theta. Really, anything would work. And so now we are looking for d theta dt. That's our target. So before we can relate the rates to each other, we have to relate the quantities. Now, we have the option of relating theta to either x or y or 10. So in a right triangle, how do you get one of the angles related to the sides? Your trig functions, right? SOHCAHTOA, or if you want to be crazy, you can use the other 3. Doesn't really matter. Let's see. We can use either x or y. We were given information about what? X or y? We were given information about x. We just found the information for y. So maybe as best practice, if you're not sure if the information for y is correct, you should try to use x instead of y, unless you're just confident in your work. Now we need to get another side involved. You can either get the y information involved, because we know it, or the constant involved, 10, which would be better. Yeah, anytime you have a constant, if you can get the constant involved, it's fewer variables, right? Which makes the problem easier to work. So what trig function can we use then if we have the adjacent and the hypotenuse? Yeah, cosine or secant if we're crazy. We're not that crazy, not on a Friday. Oh, by the way, happy December, everybody. So I'll use cosine. So cosine of theta is equal to, do I say 6 over 10? X over 10, right. X is a variable, so it's X over 10. Now you got a couple options here. You can leave it in terms of cosine and leave it as 1/10 X, or multiply both sides by 10, whatever you want to do, or you can even solve for theta by doing what to both sides? Yeah, arc cosine or inverse cosine. If you do that, you'll have theta solved for, and then you'll just use the derivative of arc cosine, which we all still have memorized, yeah? It's up to you. You want to solve for theta, or you want to do it in terms of cosine? Do it in terms of cosine? Maybe we'll try it both ways. Let's go ahead and take the derivative then as it sits. The derivative of cosine is negative sine of theta times the chain rule, d theta dt. It's real easy to forget to put d theta dt, but if you forget to put it, look what happens on the right-hand side. You get 1/10 times dx dt. If you forget to put it, you're like, man, I'm supposed to solve for d theta dt, and I don't got the d theta dt in my equation. Oh, okay. I forgot to put it there. Silly me. Sometimes I crack myself up. All right, then you go back and put it there. So we're trying to solve for d theta dt, which means we need to know what dx dt is at the moment. Do we know that? Yeah. We need to know what 1/10 is at the moment. Do we know that? Yeah. We need to know what sine of theta is at the moment. Do we know that? Not yet. Right. You can either find theta, which we really don't need. We're really interested in sine of theta. So if you come back over here and you fill in the information, at the moment we know y is 8. So once we know all three sides of a right triangle, do we not have all 6 trig functions? We do, yeah. So we can actually figure out the sine of that triangle at that moment. So let's just go ahead and plug in then. And it's the same thing. When x equals 6, colon, we get negative sine of theta. All right, so the sine ratio, sine is opposite over hypotenuse. So that's 8 over 10. 8 over 10. You don't really need theta. You just need the sine ratio. So it's 8 over 10 times d theta dt equals 1/10 times dx dt, which is still, hasn't changed, it's still 2. So now you can solve for d theta dt. On the right-hand side, we're going to have 2/10, which is a fifth. And if we multiply both sides by the reciprocal of negative 8/10, we get negative 10/8, which simplifies down to, let's see, I'll divide out to 5. Yeah, you get negative 2/8, which is negative 1/4. Good. Yeah, there's a couple ways to simplify. But you got negative 1/4, that's what I got. Okay, now, it's our final numeric answer, so trying to put units. It's theta per time, so units of angle measure per time. Ah, very good. You don't put degrees, because degrees are a very specific unit, and we haven't had any degrees introduced into our problem. So remember, if you were talking about angle measure, and there are no units, radians is a description of angle measure. So it would be radians per second. So then you can write the sentence. When the base of the ladder is 6 feet from the wall, comma, the angle between the ladder and the ground is decreasing by 1/4 radian per second. 1/4 radian per second. Okay, sweet. If you wanted to convert that to degrees, let's just review how we would do that. From the pre-cal days, that's radians per second. What would you need to multiply by to convert it to degrees? Yeah, 180 over pi. And then your rads would essentially divide out, and you're left with degrees. So if you're interested in that, and the negative's still there, if you're interested in that, you can go ahead and do that on your own. All right, if we would have done it without the cosine, let's see what else we could have done. Let me kind of sneak it in right here. You could have gotten theta equals the inverse cosine of x tenths. And now if you take the derivative with respect to t, you get d theta dt equals. And remember, the derivative of inverse cosine is -1 over the square root of 1 minus blob squared, which would be x tenth squared, times the chain rule, 1/10 dx dt. Yeah. So again, the only advantage to doing it this way is you wouldn't need to worry about what the sine ratio is at the moment. You're just going to be plugging in your x equals 6 and dx dt equals 2. But then simplifying it may be a little bit more. So it's entirely up to you. I think it's easier just to do it in terms of trig and then come over here and pull off a trig ratio at the moment. Correct. Yeah, you wouldn't need it. You wouldn't need any information about y. It's we only use the y information to get the sine ratio. Yeah. So it keeps it entirely in terms of the x info. And you could verify maybe this weekend that you get the same answer. Okay. So what else can we talk about? Well, part C. How fast is the area changing? So now we're looking at this whole region right here, and we want to know how fast that area is changing. Should the area at this moment be increasing or decreasing, do you think? Yeah, the area should increase and then decrease, because if you think about the case where the ladder is flush up against the wall, the area between the ladder and the wall is 0, right? But as you pull out the bottom, you're actually getting area, and it's getting bigger up till maybe about your 45 degree would be reasonable. After that, now your area is decreasing again until the ladder, which was up against the wall, as it goes down, it's going to actually go on the floor, right? Eventually. And when it hits the floor, ouch, but I doubt that guy will feel anything, right? Yeah, his ankles are probably going to be shattered, right? But he's still going to be like, groovy, man. Did you see the wall up there? All right, so part C, let's go ahead and give ourselves a target, part C. A for area? Yeah. So dA dt, that's our target. So before I can relate the rates, I need to relate the quantities. So in a right triangle, area is 1/2 xy, base height. Yeah, 1/2 base times height. So A equals 1/2 xy. And we can take the derivative now with respect to t. And we get dA dt equals, on the right-hand side, what rule will we use? Product. Yeah, and there's still some people that struggle with the product rule. 2 factors means you're going to have 2 terms. Take the derivative of only one at a time. So you get 1/2 dx dt times y plus 1/2 x times dy dt. Now in this case, we do need, notice, the y and the dy dt, which we've already found in part A. So if we hadn't done part A yet, we would actually have a little bit more work to go out and gather the ingredients that we need to bake this cake, or pie. It's actually pie day. Yeah.
So if we run the first question,
Mm-hmm.
you found a quantity in A that you wanted to see, you have to clarify that you got it in A.
No, actually you don't. If you found it in A, you could just drop it in here in your calculation, and the people grading your test will realize where you got it from. Yeah, you can import things from other parts of the problem. Now, does that mean that you can't put from part A as maybe a helpful guideline for someone looking at your work? No, that would be nice. That would be courteous, from part A, but you don't have to say it. Yeah.
And say, like, if you, on part A, you got a quantity that you need to use on, like, part C, but you got the wrong quantity?
Right. Then you would get, if you're still working a problem that is still just as difficult as the original one with the right answer, you can recover fully on that. They would work the problem with your wrong value to see what you get or should get, and you can get credit. Sometimes, though, if you use a wrong value and it makes the equation a lot easier, you make it a polynomial instead of a radical function, then you're not eligible for any points because you've made the problem substantially easier. But if it's the same type of problem, yeah, you can import a wrong answer, get full credit on the back end. Yep. All right, so let's go ahead and say then when x equals 6, just to denote that we're plugging it in, and we can get our answer here. dA dt equals 1/2, dx dt was 2, y was 8, 1/2 is still a half, x is 6, And dy dt. I need to go back to A. I don't remember what it was. It was -3/2. Great. -3/2. So again, if this were a free response, you're done. You don't have to simplify. But if you are finished, you need to put units on there. So units of area over time would be feet squared per second. Yeah. Let's go ahead and see what it comes out to be. You end up with an 8 there. Oops, not an equal sign. An 8 becomes a -9/2. So 7/2, negative, positive? Positive 7/2. Yeah, positive 7/2 square feet per second. So the area's rate of change is positive, which means at this moment the area is still increasing, right? Which we could have figured that out because it's still higher on the wall than it is pulled out from the base of the wall. Once those get equal, then it should start decreasing after that. So we're still at the part where the area is increasing. And then part D, what's the acceleration down the wall? So we haven't done an acceleration question at all yet. We've just been doing like velocity of quantities. So how are we going to find the acceleration of the ladder down the wall? The second derivative of, if y measures the distance along the wall, then we want the second derivative of y. Yeah. Just while we're here, what would be the acceleration of the ladder away from the wall at the bottom? 0. Yeah. If they tell you that it's being pulled away at a rate of 2 feet per second, assume that's a constant rate. So the acceleration along the bottom is 0. Does that mean the acceleration down the wall is going to be 0? No, not at all. If you think about it, what you're really doing, I'll do the side view here, as you pull it away from the wall, it's like the lever principle, right? You're moving your fulcrum out further and further and further. So as you pull it away at a constant rate, it's actually going to be doing what down the wall? It's going to be accelerating. Yeah, big time. Ouch. It's accelerating down the wall. So if the speed of the ladder down the wall is increasing and the velocity of the ladder down the wall is negative, what should the sign of acceleration be? Also negative. Yeah, because remember when the velocity and acceleration are the same sign, speed is decreasing. So we should end up with a negative acceleration. All right, so to get to the second derivative of y, I need the first derivative of y, which I think we've already done that, haven't we? Yeah, so if you come over here, you could salvage this right here. We never solved it for dy dt, but we can certainly go back and use the result. So this is part D. I'll paste it right there. All right, so now we can either take the derivative as it sits or solve for dy dt first. Do you remember which way would be easier when we were back in the implicit days? Yeah, you can leave it and then solve for the second derivative afterwards. I think it's easier if you solve for dy dt. So we didn't do this in the beginning, but we'll do it now. So I'll have y dy dt equaling negative x dx dt. And then I'll divide through, and I get y. Oops, I want to solve it for dy dt, not y. So dy dt, the velocity of the ladder down the wall, is negative x dx dt all over y. All right, so can I do anything else with this before we jump in and take the derivative? Very good. There you go. That's what I'm looking for. The same reason we didn't have to call the ladder's length L or H for hypotenuse, because it was a constant. Anything that's a constant throughout the life of the problem, you can plug in before you take the derivative, right? So right now it looks like you have 3 unknowns, but remember what we said about dx dt? It's a constant, yeah. So before you take the derivative, go ahead and plug it in. So really this ends up being negative 2x over y. And if you would have done that back in part A, then it'd be a little bit easier. You could just plug in your 6 and 8 for x and y and get the answer. If you do that, you're going to have to do the product rule on the left, which means you're going to have a dy dt in your final answer, and then you're going to have to plug in your dy dt. You can do that. I think the Hody-High rule here is going to be a little bit easier. So either way, it doesn't really matter. but I'll take the derivative like the way it sits. So I get the second derivative of y with respect to t. Remember, that's how we write it. And so now this is explicitly solved for acceleration. And over here we have the Hody-High rule. So with the negative out front, don't let it kind of get you. It's easier to associate the negative with either the top or the bottom, or to leave it out front and do the derivative behind some brackets. I think I'll just associate it with the top. So we have Ho d high. What's d high? Negative 2 dx dt. Okay? So there's Ho d high minus high, so minus negative 2x. D ho is dy dt. So we still have a dy dt in it, all over ho squared. All right, so now because it's solved explicitly, we could just plug in and have our answer. So the same thing when x equals 6. We get the second derivative is equal to, all right, carefully plugging in here, we have an 8 times a negative 2 times the dx dt, which was 2. This becomes plus 2 times x, which is 6. dy dt was negative 3/2, all over y squared, which is 8 squared. So if you stop there, you can put units. Let's keep going. I just want to make sure it ends up being a negative number. We get negative 32, and over here we get minus 18, all over 64. And you end up with negative 50 over 64, which is negative 25 30-seconds. And now the units are going to be what? Feet per, yeah, it's velocity. So feet per second or feet per second squared. And yeah, notice the acceleration is in fact a negative number. And we knew that because the speed was increasing and the velocity was negative. So what's nice about this problem is it's just one simple little situation, but there's lots of different things that can be asked about it. So anyway, Pythagorean theorem shows up quite a bit in related rates. You could also optimize the area under the ladder, which without proving it would be when the x and y are the same, right? When you have your isosceles. Yeah. Okay. Any questions on example 5? All right. See you guys next year or next period. Okay. Example 6. This is kind of like what we did to start off the section. A spherical balloon is being inflated at a constant rate of 5 cubic inches per minute. When the radius of the balloon is 4 inches, how fast is the surface area changing? We had that question in the beginning. All right, so drawing a picture. There's a blue balloon. Here's the part where the air goes in. Now it's being inflated, not deflated. So what is the critical variable in a sphere? The radius, yeah. So we'll call it little r. Seems reasonable. The snapshot moment, when the radius was 4, so that's when r is 4 inches. There's your camera. How fast is the surface area changing? So we're targeting dA dt. We want to figure out how fast the area is changing. Bless you. And there's one other thing. It's being inflated at 5 cubic inches per minute. So that's the rate. So that's the rate of change of what quantity? Volume. Yeah, look at the units if you don't know. Cubic inches is a measure of volume. So we can call that V for volume. So dV dt is what kind of 5? Positive or negative? Positive, yeah, because the volume is increasing. We're inflating it. Had the balloon been deflating, then that would be a negative number. Okay, so here we go. We want to be able to eventually relate the rates of volume to the rate of change of area, but before I can do that, I need to relate volume to area. How can I relate those quantities? What's that? Yeah, there you go. There's probably not a formula that you memorized that gives you the volume of a sphere in terms of its area. But you do know the volume of the sphere in terms of the radius, and you do know the area of the sphere, the surface area in terms of the radius. So let's go ahead and just write down two equations here. The volume is 4/3 pi r cubed, and I know you know that. And the surface area, A, is the derivative of that with respect to r. It's just 4 pi r squared. Okay? So you have two options here. Because you have V in terms of r and A in terms of r, you can actually solve for r and get V in terms of A directly, which would be your option. Or you can just work with two equations and then find the value for one and plug it into the other. What do y'all want to do? The more work option? Well, the only thing is if you solve these for r, you're going to have a cube root and a square root. So you'll have radicals in your equation. Yucky, yucky, gross, gross. Yeah. So let's see how far we can get without making volume as a function of A. Let's take the derivative of both sides. d dt. Here we get dv dt equals 4 pi r squared times dr dt. And here we get dA dt equals 8 pi r dr dt. So now it actually might be a little bit easier. We really wanted to relate their rates to each other. So notice now they both have dr dt in it. Now might be the time to actually put v in terms of a, or dv dt in terms of dA dt if you solve for dr dt. But you still don't have to. You can evaluate one and plug it into the other. What do y'all want to do? You want to put them in terms of v in terms of a? All right, so let's do that. This one, if you solve for dr dt, it's kind of like substitution in algebra 2, but we're doing it with derivatives. So if we divide through, we get dv dt all divided by 4 pi r squared. And over here, we get dr dt is equal to dA dt divided by 8 pi r. And since those are equal to the same thing, by the transitive property or substitution, they should be equal to each other. So I'll come over here. So dv dt, bless you, all over 4 pi r squared is equal to dA dt over 8 pi r. And now you can plug in and then solve, or solve and then plug in. Because you have pi's and r's on both sides, I would probably, in this case, I'm kind of curious what this would look like if we go ahead and just keep going. If we're looking for dA dt, it should be easier to solve for dA dt. So let's go ahead and just multiply both sides of this expression by 8 pi r. 8 pi r there, and 8 pi r over here. And so these will divide out. We're left with dA dt equals 8/4 is going to divide out, so you're left with a 2 in the top. Your pi's divide out completely, so you have 2 dv dt divided by, in the bottom, you're left with the 8 and the 4 divide out to give you 2. You're just left with a single r, right? One of the r's in the top divides out with one of the r's in the bottom. So there you go. It was easier to relate them to each other in the same equation after the fact rather than before the fact. And now you could just plug in. So now you could say when r equals 4, you get the surface area dA dt is equal to 2 times dv dt, which we said was 5. That was given, all over 4. And that gives you 10/4 or 5/2. And the units are going to be area per time, area per time. So that's square inches per minute. Square inches per minute. So this is about as complicated as the related rate questions get, where you don't have, from memory, a single equation that relates to quantities, but you know you can relate them by some other thing. Now, if you wanted to, you could just plug in. You could have plugged in on dv dt. You could have said 5 equals 4 pi times, 4 squared. And then you could have solved it for dr dt. You get a number for dr dt, and then you can go back over to this equation then and say, so now dA dt is going to equal 8 pi times the radius of 4 times the dr dt that you found over here. So that would be like a 2-step process instead of doing it in a 1-step process. Whatever you think works better for you. Whatever inflates your balloon. Okay. Questions or comments on example 6? So that was the most work we've done on a problem to get one answer. So just keep telling yourself, man, that was a lot of work and it was kind of bad, but it still was an optimization, right? Okay. Example 7. 2 cars are riding. Cars ride on roads, I guess. 2 cars are being driven, hopefully, by either a real person or a computer, on 2 different roads. Oh, okay, that's nice. And the roads meet at a 90-degree angle. Car A is 3 miles south of the intersection, traveling north at 40. Car B is 2 miles east of the intersection, traveling east at 50. How fast is the distance between the 2 cars changing at this moment? All right, let's draw a picture. What do you want the first car to look like? A what? A car like this? Okay. And then the other one's going to be a truck full of pumpkins. Is that what we mean by drawing a picture? Yeah, it's the pumpkin farmer. Okay, no, let's just draw a schematic. We have 2 roads that are intersecting at 90-degree angles. All right. Car A is 3 miles south. Car A is 3 miles south. So I'll just let A represent the distance that car A is from the intersection. It's 3 miles south. Traveling north. So that's dA dt. Traveling north, that's its rate of change by 40 miles per hour. Okay, that's cool. Car B is 2 miles east of the intersection. So he's right here. I'll let B be the distance that B is from the intersection. And he's 2 miles east, traveling east. So he's moving this way, and this guy's moving that way. He's traveling east at 50 miles per hour. So dB dt should be something with 50. Now, the snapshot moment is when A is 3 and B is 2. There's the snapshot moment. Now, before we go and set it up, we need to make sure that our rates are the correct sign. Because all I did is I labeled them as speeds, not velocities. Should dB dt be positive or negative? Positive. Why? What is happening to B in reference to the stationary point, the intersection? It is increasing because he's moving away from the intersection. The distance B is getting bigger, so dB dt is positive. What sign should dA dt be? Negative. And this is what throws some people for a loop. How can it be negative if he's going up? I thought up was positive. Yes, but I only drew it going up. You're really levitating over the ground looking down on a flat plane, right? So because A is decreasing, he's getting closer to the intersection, the dA/dt should be a negative number. Very important. Okay, so now, let me move this A to the other side. Now I want to know at that moment, how fast is the distance between them changing? That would be as the crow flies. So if I connect those two, I'm looking for that distance. Not the distance around the corner, just straight through. We need a letter for that. What do you want to call it? If you call it D, call it Big D, right? How about Big D last night? Wasn't that a game? Yeah. Snapped a 3-game skid. Yeah, Big D. Don't use little d because that's the derivative. So our target now is dD/dt. dD/dt. Or you can call it C, dC/dt, whatever you want. All right, so now we need to relate their rates, but first relate their quantities. All of these are variables, right? Unlike the ladder problem, which was actually the previous problem, I meant ladder like DDER, the hypotenuse was a constant, so we just called it 10. Here we have a hypotenuse of D, but it's changing as well as the two sides. But the Pythagorean Theorem does a good job of relating them still, right? A squared plus B squared equals D squared. So there's your position equation, quote unquote. And now if you take the derivative of that with respect to T, you get dD/dt. And again, you also could at this point solve it for D. If you want to try that one time, see if you prefer it, you'll just have a chain rule with the radical. I'm going to do it without it. So I get 2a dA dt plus 2b dB dt equals 2d dd dt. 2d dd dt. 2d dd dt. And not surprisingly, the 2's can divide out all the way across, making the numbers easier. So we have 6 unknowns, and we are looking for d dt. So let's go through and take inventory, see if we have all the necessary ingredients for this calculus pi. We need A, B, and their rates at this moment. Do we have all 4 of those? Yeah, those were given. The one thing we don't have is the D value at this moment, which everything up to now has been a nice, easy 3, 4, 5 right triangle or a dilation of it. Is this the same thing? Probably not. So let's go ahead and find D at the moment by plugging it into the Pythagorean Theorem. And then if you want, you can add that info to the camera at the snapshot moment. So I've got 3 squared plus 2 squared equals D squared. So D is equal to the square root of 9 plus 4, which is 13. Does that simplify? No, it's just the square root of 13. Okay, sweet. But now we're ready to go. So now we can kind of plug everything in. So we'll say, referencing a moment in time. So I'll just say when A equals 3, we get 3 times dA dt, which is negative 40, plus B at the moment was 2 times dB dt, which is positive 50, equals the square root of 13 times dd dt. It's kind of hard looking at it right here to know if D is going to be increasing or decreasing based upon where they are, but the numbers won't lie. If we solve for d dt, our numerator on the left simplifies to negative 120 plus 100, and then we divide through by the square root of 13, so I'll go one step further and simplify it. You get negative 20 over the square root of 13, and now the units are units of distance per time, which would be miles per hour. So if you want to do miles divided by hours, that's fine. You can also do the Americanized MPH, which is fine. So the distance between them is actually whating? Decreasing, yeah. So the sentence would be, when car A is 3 miles south of the intersection, comma, the distance between car A and B is decreasing by 20 square root of 13th miles per hour. All right, comments or questions on that one? Let's see how many examples we have left. Not enough? Not enough for what? We got 4 left. Okay, I think that makes for a full Monday, don't you? The reason I want to kind of stop here is because the next 2 problems are cone problems, and I want to be able to work both of them in the same day because cone problems are kind of important. I guess we could jump ahead to, but it's Friday. But it's also the start of a new month and the end of a week. All right, let's just stop right there, and we'll talk about sand on Monday. Ooh, that's mouth-watering. Sand. We'll get to the snow cone.